when we were working with the multivariable chain rule, we noticed that for this particular situation where we have a function with two input variables and a function, a vector valued function that gives us a position, in this situation the chain rule ended up looking like this, but we noticed that this looks like a dot product. It looks as if we took the dot product of so that dx dt and dy dt, right? It looks like we took the dot product of that vector dx dt and dy dt. It looks like we took the dot product of this with some other vector, but that vector would sort of have to produce these partial derivatives. So this would be the vector partial f partial x, comma, partial f partial y. Right? And this part here, this is just the derivative of our vector valued function with respect to t. So what we recognized is that this particular chain rule, it produces this sort of new vector. And it's not really clear what this vector means, but since it shows up in the chain rule together with the derivative of r, it must be important. So let's give it a name. This vector gets called, so it's this upside down triangle f. Okay, and this is pronounced the gradient of f, is how this is pronounced. Sometimes this symbol on its own, the upside down triangle, is called nabla. Sometimes it's called del, but this collection of symbols is called gradient of f. So we've invented this new thing called the gradient of f. It's the vector made up of partial f partial x, partial f partial y. Of course, if we were in a situation where we had more input variables like x, y, z, then the gradient of f would be, it would be a three-dimensional vector where you have one partial derivative for every input variable, right? So in general, the gradient is just the vector of all the partial derivatives, like this. And if you had more input variables, you'd have more dimensions in your gradient vector. So that's fair enough. Now we can write that in this particular situation that we were working in, the derivative of f composed with r of t is, so that time derivative would be called df dt, and we can write it as the gradient of f dotted with dr dt. And I mean, that's fair enough, but that doesn't really tell us what this gradient of f thing is measuring, right? We see that it's showing up in this formula for the chain rule, but that doesn't mean we understand what it means. So let's see if we can figure out what it means. One thing that is making this a little difficult is that this derivative, df dt, right? If we have some graph like this, and we're moving across the graph, right, maybe, around here and then over the backside and then out there, the rate of change of f with respect to t as we move along our path, that's made out of two pieces. It's made out of like how fast the height of the graph is changing, like how steep the graph is under our feet, and also the other part of df dt is how fast we are moving across the graph, right? Because df dt, that's the slope of the graph at our location, that could change either because we are moving faster or because the actual geometric shape of the graph is changing. So, if we want to get at what the gradient of f actually means, we should keep only the part of this derivative that is actually talking about the slope of the graph, and we should throw away the information that has to do with how fast we move across the graph. Well, in general, the rate of change of a function with respect to time, it's the slope of the graph times the speed that we move across the graph, right? So if you imagine a single variable situation, and so now we have a function that is a function of a single variable, and then we have our position is some function of time. In this single variable situation, the chain rule says df dt is going to be df dx times dx dt, right? That's just a single variable chain rule. And dx dt is just telling you how fast you move sideways. And df dx, that's really the slope of the graph that you're walking across. So in general, the rate of change of a function with respect to time is the slope of the graph times the speed that we move across the graph. If what we are interested in is the geometric, or if what we're interested in is just something having to do with f, right, because the gradient of f doesn't involve time, only the function f, then we should throw away the information about how fast we are moving across the graph and only keep the geometric information about f. In other words, what we ought to do is we should take this and divide both sides by the speed that we are moving across the graph. So that when we do that, so this df dt, this is gradient of f dotted with dr dt. So the right-hand side is the slope of the graph times the speed that we're moving across the graph. But the speed that we're moving across the graph, that's the magnitude of r prime, right? So now if we divide both sides by the magnitude of r prime, something kind of nice happens. On the right-hand side, those cancel, and so we're just left with the slope of the graph. And on the left-hand side, well, we could sort of group dr dt with its own magnitude here. So we get gradient of f dotted with r prime over magnitude of r prime, right? R prime is just another name for dr dt. So the slope of the graph is given by this gradient vector dotted with r prime over length of r prime. And right, remember the interpretation we have for a vector divided by its own length is that this is just the direction of r prime. Dividing r prime by its own length sort of throws away the information about the magnitude of r prime and only keeps the direction of r prime. Okay, so what this dot product is computing now is just the geometric slope in the direction of r prime, right? So to kind of make sense of this, let's figure out what the units are. So let's introduce some units. If this function tells us the temperature of some metal plate at the position xy on the metal plate, right? So if we have some metal plate sitting here and we're at a point, and we're moving in some direction like this, so this is the direction of r prime. Let's write down what are the units for partial f dot, or for a gradient of f dotted with dr dt. So on the one hand, the gradient of f, remember that's partial f partial x, comma, partial f partial y. Dr dt, that's dx dt dy dt. Okay, so these partial derivatives, partial f partial x and partial f partial y, so f is producing a temperature, which I should have said, let's measure that in degrees Celsius. X and y we're measuring in centimeters, so this derivative, it's going to have f units per x units. So that's going to be degrees Celsius per centimeter. And same thing for partial f partial y, that's also going to be degrees Celsius per centimeter. Now when we dot this with r prime, well, these two derivatives, so here we're just looking at units. For these two derivatives, well, x is measured in x and y are measured in centimeters, t is measured in some time unit, let's say seconds. So we get centimeters per second. Okay. So that's what the dot product gives us. But now let's, and when we do this dot product, right, the units in the first factor, degrees Celsius per centimeter, get multiplied by the units for the right-hand factor, and we get degrees Celsius per second, which makes sense. This is the unit for dF dt. But now let's look at the units that we get when we divide r prime by its own magnitude. So now we're going to look at the units for the gradient of f dotted with r prime over the magnitude of r prime. Okay, so gradient of f, we've already seen that the units for that are degrees Celsius per centimeter. And then derivative of r, that is in centimeters per second, divided by, and then the magnitude of the derivative of r, that's also in centimeters per second. Right? This denominator here, this is the speed, and that also is in centimeters per second. So the centimeters per second cancel, and the units we get are degrees Celsius per centimeter. Right? And if we look at f, actually, I guess, sorry, not f, but the partials of f, right? This unit, degrees Celsius per centimeter, those are the same units as the partial derivatives of f. Also, if we had the graph of f, so some graph, right, a slope on that graph would have height units divided by horizontal units. And height units are output units for the function, that's degrees Celsius, per horizontal units, but we're measuring our horizontal quantities are positions, so that's going to be measured in centimeters. So the upshot of all of this is that this quantity is telling us it has the appropriate units to be a slope on the graph, and right, this analysis that we did up here, right, gives us a second reason to think that this dot product, where we're dividing by the magnitude of r prime, is telling us the slope of the graph in the direction of r. So these two things together indicate that what we get when we take this, when we take the dot product of the gradient and r prime, or the gradient and some vector, and divide by the length of the vector, what we get is actually the slope of the graph itself. Right? We've sort of thrown away the information about how fast we are moving across the graph, and we only have information about the geometric shape of the graph, and that information is the slope of the graph. So for this reason, this quantity we will call the directional derivative of f in the direction of some vector. So we'll write it this way: capital D sub v of a function f, and it is the gradient of f dotted with the vector v over its own magnitude, and this is the slope of the graph if we move in the direction of v. Right? And what matters is the direction of v. Because we've divided v by its own magnitude, this vector here is actually a unit vector. And remember, unit vectors represent sort of pure direction. Right? So that's why we get a slope and not a rate of change with respect to time. Right? Time is out of the picture because we've divided by the magnitude of v here. And what we're left with is pure geometric information about the shape of the graph of f. Okay, so for an example, let's find the slope of the graph of this function at the point -1, 0 in the direction of the vector 3, -4, and also the direction -3, -4. Okay, so since we want the slope of a graph in certain directions, well, that's one of these directional derivatives. So let's calculate the directional derivative in the direction of v first. So we need to calculate the gradient of f. So let's see, partial f partial x is going to be our first factor. So derivative of this with respect to x is going to be minus cosine y over x squared. Okay, and then the partial derivative of f with respect to y is going to be minus sine of x over minus sine y over x. Okay, so there's our gradient vector. Now we need to dot that with v, which is 3 comma minus 4, over the magnitude of v. So magnitude of 3 comma minus 4. Also, notice that, this gradient vector depends, what this gradient vector is depends on where we are located, because x and y shows up in the formula for the gradient of f. So we need to evaluate this at the point that we're located at, and the point that we are at is minus 1, 0. So let me put one of our vertical evaluation bars here to indicate that we're evaluating this at the point minus 1, 0. Okay. All right, so now we'll plug in our point minus 1, 0. We get minus cosine of 0 is 1 over minus 1 squared is 1. And then in the y direction, we get minus sine of 0, which is 0, over minus 1. Okay, and then let's see, this magnitude in the denominator is 5, I think. Right? Okay, so we can pull this scalar multiple of 1 over 5. We can pull that all the way out front and just do the dot product of minus 1, 0, dotted with 3 minus 4. And that's going to give us, so 1 over 5 times, and then minus 1 times 3, so minus 3, plus 0 times 4, that's 0. So altogether, we get minus 3/5. Okay, so in the direction of v, this graph is going down with a slope of 3/5. So let's look at a picture of this graph. So here's a picture of the graph. I have the point that we're working with marked right here. Let me zoom in a little bit. And actually the xy plane is kind of in the way. I have the point on the graph corresponding to our point minus 1, 0. The corresponding point on the graph is down here. It's labeled B. But the xy plane is in the way, so let me get it out of the way there. Okay. And this vector here is pointing in the direction of our vector, whatever the vector was, 3 minus 4. Okay. And let me actually, I need to zoom out so that we can see what is happening in this direction. If we sort of turn this graph to get a few different perspectives on what's happening here, as we move this way, so along our vector, you can kind of see that the graph is going down a bit. Right? This empty patch here, that's just an artifact of the fact that GeoGebra isn't graphing. GeoGebra is sort of cutting the graph off at a lower limit. In fact, the graph continues downwards further, but we just don't see that part of the graph. Okay, it's a little easier to see what's happening if I actually draw the curve on the graph that goes along this direction. So I have that right here. Okay, and if we look at this from a few angles, you can see that in this direction, this curve is going downwards, right? So that means that the slope of this line is definitely negative as we move in this direction, in the direction of our vector, right? Which from this perspective is from the right to the left. This line, this curve is going down. So the tangent slope on this graph is, well, it's definitely negative, and it doesn't look like it's quite minus 1. So minus 3/5 seems plausible. Okay. So that's for the first vector. Let's look at the other vector. Remember, we had another vector which was the other vector was w. So let's find the slope of this graph in the direction of w. Okay, so since we're at the same point, the gradient vector, once we evaluate it at our point minus 1, 0, will still give us this same vector. So minus 1 comma 0, but our vector w this time was minus 3 comma minus 4. So we need to divide that by the magnitude of minus 3 minus 4. Okay, that magnitude again is 1/5, so let's pull that out front. And so we have 1/5 times minus 1, 0, dotted with minus 3 comma minus 4. And this time this comes out positive. It turns out it's positive 3/5 this time. So let's look at the graph again, but let's look in this direction, minus 3, minus 4. So here's our graph again. Let's get rid of that. Let's get rid of the first direction we looked at. Let's look at this other direction. Okay, so there's the vector in the direction we're looking at now. And if you imagine going this way across the graph in the direction of this arrow, right, if we look at it this way, sorry, maybe this is the right way to look at it. So we're starting at this point B and moving sort of away and leftwards. We're sort of climbing up out of this valley, going up this way. Okay, so again, let's look at the curve in that direction. It looks like that. And, you know, if we take the side view of this, then yeah, it looks like this as we move leftwards to rightwards, which is the direction this arrow is pointing. The slope of the tangent line to this blue curve, it's definitely going to be positive, and it looks like it's not bigger than 1, so 3/5 seems plausible. Okay. So if we want to know just geometric information about a graph, we can calculate a directional derivative, which looks a lot like that dot product form of the chain rule, except we're dividing our vector by its own magnitude so that we're getting pure geometric information instead of mixing together geometric information about the graph and speed information about how we move across the graph, right? So this, by dividing by the magnitude, we're only keeping the direction in which we are traveling, and so we extract geometric information about the graph of f in that direction. That's what we're calling the directional derivative.